Hey, welcome back to discussion 26. Let's get started with problem number 15, page 517. So we're given a wave function. It describes a transverse wave on a rope. X and Y are in meters and seconds. So what that's telling us is we have a wave on a rope. It's like probably tethered at the ends. Right, this is two-dimensional. We're going to have a Y direction, which is this, and then we have the X direction. So the wave is traveling this way, which is described by this, right? Okay, we need to find out what is wavelength, period, and then the speed, transverse speed of the wave, and then also at part D is at time t, what is the transverse velocity of a rope element located at 2 meters, and then at time 1 second as well. We also want to find the acceleration of a rope element at 2 meters. So similar parts. Let's get through the first three things first. So those are actually rather easy to do. Okay, so let's recall, before we get to part D, let's recall what is the general form for a wave function, right? So we have y of x and t is equal to some amplitude, oftentimes called y max, times sine kx minus omega t. It's slightly different than for your simple harmonic oscillators. Now we're describing wave kinematics, and the derivations for these are also in the book, but this is essentially the same thing. Okay. So now k is going to be your wave number, right? This describes the direction that it's traveling in the x direction. Okay. So what is k for wave number? We have a relationship. It's similar to period and angular frequency. It's 2 pi over lambda, okay, where lambda is your wavelength. That means that lambda wavelength is equal to 2 pi over k. Well, what is k in our problem? Remember, whatever coefficient we have times the position is going to be your k, right? So in this situation, here's x, 3 pi. K is 3 pi. So that means that we have 2 pi over 3 pi. That cancels. We get 0.6 meters, because it's a wavelength, okay? So that's lambda. Next, we need to use our relationship between period and angular frequency, just like I was mentioning before, to find period, right? Because that's what we're asked to find. So, good one. Okay, so now we have pi over 4 is going to be equal to this omega, right? So let's figure out what that's going to be. Omega is equal to pi over 4 in this situation, which means, well, we also know the relationship between t is equal to 2 pi over omega for an oscillator. So we just plug it in. So 2 pi over 4. Those cancel. That gives you 8 seconds. Okay, so that's part A, that's part B. Part C, we're asked to find the velocity, rather the speed of the wave, which we have as Vx, right? Vx is going to be equal to the angular speed over the wave number. And so now we know what both of these are. We could just plug them in analytically. Pi over 4, what was k is going to be 3 pi, right? What was it? 3 pi. Ah, that's what it is. 1 over 3 pi. Okay, that cancels. You get 1 over 12. That gives you a value of 0.083 meters per second. The units work out on this because we have, this is in radians per second. Radians is essentially just some number, right? Or we say it's angular frequency. That's what we actually call it in this situation. So it's 1/seconds. And then K is actually in units of 1/meters. And so that gives us 1/meters. That goes on top, meters per second. That works out. Okay. Now let's look at part D. Part D. Okay, we're asked, okay, so we're given a time, t is equal to 1 second, x is equal to 0.2 meters. And then, what is the transverse velocity of a rope element located at x equals 0.2, right? Okay, you're right, whatever. So, let's look at what we just found real quick, just to kind of clear things up a little bit. So this is wavelength, right? We had 0.6 meters. This is wave length. We had period. We had the wave period. This was what, 8 seconds, something like that. And this was velocity of the wave. So we had the wave speed. It's not velocity, excuse me. It's the wave speed. That was 112 meters per second. So here we have a few different quantities that describe the motion or describe properties of the wave itself. Right? Now we're looking for transverse velocity. So we have this wave function. This would be, so we can describe a wave as one of two ways, right? So here's like, let's call this wave, this is the wave. Well, let me draw a better wave. Here's a wave. If the wave oscillates in this direction, right? If it's oscillating in this direction, but it's traveling in this direction overall, this is the transverse velocity, right? Transverse, well, you know, transverse velocity. And this is essentially the function that we're given. I mean, we're given this position, so we can just take the derivative of this to figure out what is the transverse velocity. Alternatively, the other option that we have is if the wave looks like this, it doesn't necessarily even have to be like sideways. I mean, it could just be the same wave. So let me just pull this back down here. Now the wave is oscillating in this direction, but it's also now it's traveling in this direction or this direction. This is longitudinal, right? So that would actually be the longitudinal velocity of the wave. Okay, so that's what we're talking about. So we want to know the overall velocity of the wave as it travels down the rope. So let's get started on that. What is our function? Here, let's copy this thing so I can see it. So that means that v of xt is equal to negative, nope, it's not negative, it's 3 pi, sorry, pi over 4. We're just doing this with respect to time, right? So we're actually taking dy dt, right? That's what we want to do. Okay, so that actually gives us then pi over 4 times 0.05 meters times cosine 3 pi x plus pi over 4 times time. And then we just plug it in. So we just say v of, what was it? It was 0.2 and 1 second. That gives us this. 3 pi times 0.2 plus pi over 4. Plug that into a calculator. And we get a value of negative 0.035 meters per second y hat. So one thing we should mention, and that I neglected to actually write down is that this should be a negative sign, and the reason for that is because we have a negative omega over k, because right, our basic form is minus omega t, and we're actually given positive omega t. Right, so the only thing that really changes here is going to be the direction that we're traveling. So that's what this means. So like a normal wave traveling, let's say positive x hat, or yeah, like this way, or even positive y hat, I guess, if this is y hat, is going to be the point I'm trying to make is this is negative in general, and then we're given the value in positive, and so that's going to change things just a little bit. And because I'm not doing a great job of explaining this, I recommend looking at the book. Equation 17.10. 17.10 equation is Vx is equal to negative omega over k. Okay? If you just scroll up the page a little bit on page 494, it talks about the speed of the harmonic wave. Also in that section you have transverse versus longitudinal harmonic waves. And so I just recommend giving that a look, just so you can sort of better understand why this ends up being negative here, okay? All right. So, and the reason I went into that now is just because we ended up with a negative value, and I wanted to make sure I was clear about what was going on there. So then for the next part, we pretty much do the same process, and we're asked to find acceleration. So we take another derivative, right? dy squared dt squared is equal to dv dt is equal to a. And so that's what we want. So let's take this again. So we're going to have pi over 4, and this is going to be squared. This is also going to be negative because we're taking the derivative of a cosine function, of a positive cosine function. So this is going to be negative. A is equal to negative pi over 4 all squared times 0.05 sine 3 pi times 0.2 plus pi over 4. This is in the y hat direction. And the reason this is in the y hat direction here is because if we look at our basic wave equation, this is going to give you, so this tells you what direction the wave is oscillating, right? So let's see if I can, here, let's take this. So if we have, let's call this, we're just going to flip our axes. Well, we can maintain here. Here's y hat, here's x hat. So we're told now that this thing is oscillating in the x hat direction given by this, right? So that means that we have some oscillations going this direction and then this direction. Okay? So it's more like this. Right? Oscillating in the x direction, we're looking for a y position. So that means that it's oscillating this way, but it's in motion this way. So this is a transverse harmonic wave going this way, oscillating here, traveling here. So we're in the positive direction here. Okay, hopefully that makes a bit of sense. Again, there's more about it in the book. Okay, so if we just plug this in, oops. Oh, I already did. This gives us a value of negative 0.014 meters per second squared in the y hat direction. Next problem. We're looking at number 24, page 517. Number 24. Okay, so we are asked to find the propagation speed of a wave. We're given this wave function. It's on a thin wire. And so the propagation speed is going to be the same thing as the wave speed. Okay, so we have some relationships that we can use to solve this. We know that this is going to be equal to the angular frequency over the wave number. Just remember that this was in units of 1/meters, and this is 1/second, so that gives us units of meters per second. So we can just do that directly. I think that should work. And then we have a value of 46.7. Remember that this is negative in the negative direction if we're given positive values in the sine function. Okay, so that's omega, 4.35. So this gives us a value (10.73 meters per second. We are then asked to find the tension in the string. And so in the summary, again, I'm not going to go through all of the derivations, but in the summary we're given this value that this Vx is equal to omega over k. It's also equal, for a situation like this, we have square root of the tension force over the mass density. Okay, and we're given a mass density, so we can just solve directly. So we can take this and solve directly for the tension force, or the magnitude of the tension force. Okay, so then we have 10.73 meters per second, and it's all squared, times mass density of 3.2 e to the negative 3 kilograms per meter. Right, and that's pretty much it. And then you just plug that in, and you get a value of 0.368 newtons. Right, let's just check the units real quick. Here we have meters squared per second squared. This is kilograms per meter. So that's kilograms per meter, meters squared per second squared. One of these cancels, that's a newton. Cool, so that works out. The derivation for this relationship is given to you on page 495, just in case you want to check that out and see why we can actually do this. It's kind of an interesting, to go through it. So I recommend it if you have an interest. Okay. Next problem is number 70. Okay, for the next problem, number 70, we're given a wave equation, position function with using a wave, right? And then we are asked to find amplitude, wavelength, and angular frequency. And so that's going to be something that maybe is a little more tricky than normal, because if you notice, this is a squared sine function. And then it tells us that we're going to need to use an identity, which is cosine 2 theta is equal to 1 minus 2 sine squared theta. So it says find amplitude, frequency, and wavelength and use this identity. So we can do that. It's not too bad. All right, so first thing we got to do, if I can get this to work, is so let's solve for sine squared theta, because that's what we have, right? We're given a function of sine squared theta. We can use this and then put everything in terms of this other stuff. So that's going to give us cosine 2 theta minus 1 all over 2 is equal to negative sine squared theta. So then sine squared theta is equal to 1/2 minus cosine 2 theta over 2. Right? So then we just plug that into the function, and that's pretty much all we got to do. So then y is equal to 0.5 over 2 minus 0.5, because that was out front, right, over 2 again. And then cosine 2 times everything that was inside the function, which is 2 times x minus 4 times t. And so again, well, let's do this. So we have 1/2. 1/2 times 1/2 is 1/4. And then, so that means we have 1/4 times everything. So now y is equal to 1/4, 1 minus cosine 4x minus 8t. Right. So amplitude is just going to be similarly to how we had this coefficient out front here, 0.5, in front of this function. It's pretty much going to be the same thing as what we have. It's this coefficient in front of this function. Or this, you could say it's this coefficient in front of this function, right? Because we use this identity here, we were able to kind of simplify in terms of cosine, something we can actually use. And then so amplitude is going to be equal to I'll call it 1/4 is equal to 0.25 meters. That's what I say. And then so lambda, wavelength, is equal to, what do we have, 2 pi over k, where k in this case is 4. 2 pi over 4, so this is equal to pi over 2 meters. You could also say that's 1.57 meters. Okay, next we need omega. Omega we can put in terms of, well, we just have it here. It's going to be 8, right? So this is 8. We'll call this 8 1/2. It could be radians per second. Okay, so that's pretty much it. So the main thing that we had to do was just rearrange using some algebra given this relationship. Okay, and it did make our function look a little different, but the amplitude, the general concept of the amplitude is still the same. It's the coefficient out front of the function, and then we had this was k and this was omega. So next problem. So for the next problem, we're given a wave function, y max sine of 2 pi times x over a minus f times t, right? We are told that v max is equal to d dy dt, the maximum value, right? And we're also told that this magnitude of the maximum speed is equal to 3 times the propagation speed. The propagation speed would be v, we call this vx. And then we're asked to find the value of a in terms of y max. So find a in terms of y max. So this is the a that we're looking for. This is a constant. This f is the frequency, we're told. And so let's remember what we're actually looking at here. We can sort of do some simplifying if we just kind of multiply 2 pi through, and then we can find what relationships we're looking at. So for a normal wave function, we're told that we have, what is it? It's k times x minus omega t, right? So let's take what's in this sign argument and set it equal here, so we can kind of look at what we got. So kx minus omega t is equal to 2 pi over a times x minus 2 pi f times t. Well, that implies directly that k is equal to 2 pi over a. And also that omega is equal to 2 pi f, which is our standard relationship. So that makes sense. So that's good. So I'm sure we can use some of this information. Let's also remember that the general form for a wave speed is Vx is equal to omega over k. Okay, also, the general form for Vmax is equal to omega times y max. So I think a lot of this stuff will be useful. Okay. Well, already we're told that, I mean, this was given to us in the problem statement, right? We have Vmax is equal to 3 times the wave speed. So here we have these two relationships. So let's write these down. So Vmax is equal to 3 times the wave speed. All right, so here's the wave speed. Oops. Here's our wave speed. Here's Vmax. So what does that mean? Well, that means that omega y max is equal to 3 times omega over k. And k was, what was it? It was 2 pi over a. Right? We could use this, but I don't think that we're going to, considering that this is here and this is here. Those cancel. So now we have y max is equal to 3 over k, which is equal to 3 times a over 2 pi. Right? We want to find a. That's what we're after. That's the whole point of this. So now a is equal to 2 pi over 3 y max. And that's the answer. So it was helpful. So this problem actually was helpful to just kind of lay out what you know. So take all this stuff in the argument, put it into a general format that you can recognize, and then you have your k, your omega. And then we also had these relationships that were, so I think one of these, this one was from the last chapter. But it might also be listed in this chapter as well. But this was from, if you remember, where we had y is equal to y max sine something, v was equal to omega y max cosine something. Something like that. And then so what we said was this was Vmax. If this was y max, this was Vmax. Next problem. So the next problem gives us a wave function, as usual. This is a wave on a string, right? And we're told that we want to find at which values of time, like at which values would we measure the time for the position to be 0.3 meters for the wave. Right? So let's recall that since this is a wave, this thing is oscillating, right? So we're looking for, at what point will this be back at 0.3 meters? Or I guess you could say, you know, I think this is for like a, in general, if you take a rope, oh, that's not what I wanted to do. And you kind of like do this thing with it, you're going to get a wave that travels down the rope. And that's what's happening here. And so we want to know, where is this going to be back at 0.3 meters? Right? Okay, so first thing we can do is say, well, y is equal to 0.3 meters is equal to 0.4 sine of all of the stuff in the argument. Cool, and then we just solve for t. So let's find out when the first time is going to be. So this is going to be 0.3 over 0.4. And we'll call this, let's move this down. We'll say that we need, what is this, sine inverse, or arc sine. Right, and this is going to equal 4 times x plus 25t. So that means that we have arc sine 3/4 minus 4. What was it? This is also, by the way, we're told that x is going to be 0.1. So this is going to be 0.4 minus 0.4, and then we take 1 over 25. That gives us t. We'll call this t1, because this is going to be the first time that it's at 0.3 meters. Okay, well that's easy enough. So we just plug that in, and then so we get a value for t1 is equal to 0.0179, and this is going to be in radians. Well, it cancels actually. So yeah, so actually we're in seconds. We can show the units by just sort of looking at what we got going on here. So this is in meters. This amplitude is also in meters. So those cancel, become unitless, which is what we would want in a sine function, right? This is k times x. K is in units of 1 over meters, right? This is 1 over meters. So 1 over meters times meters, that cancels, that's unitless. And then we would also expect this to be unitless as well. So this omega is in units of 1 over seconds. So since we have units of 1 over seconds, we take that to the other side. 1 over seconds gives you units in seconds, and everyone's happy. So the next thing we can do is we want to take this this general sine, this arc sine argument, because this is something we can use in trigonometry. We can say, all right, well, what is the next time that this is actually going to happen? Or at what point, at what phase, right? So we have a phase shift of pi, and that's usually what we look at, right? We have 0, and then there's pi, and we want to say, well, so if this is the first time, what is the next time? We're going to take pi minus this value in radians, or rather 180 degrees minus, what did we have? It was, oh, we have to look at it. I don't have that yet. So whatever this happens to be, we'll call this theta naught. 180 minus theta naught in degrees. And that's going to give us something that we can use. Oh, there we go. That's what I wanted. Okay, so we found the first time. What I'm saying is that we need to take this value, figure out where this is at. Okay, so what is the first position? So what does this equal? This equals let's see. This equals, so here this is going to equal 0.848 radians. Right, so theta naught is equal to 0.848 radians. So then we could just do, I guess since I wrote this in degrees, I was expecting, well, let's just write it out. So this is going to be pi radians minus 0.848 radians. That gives us a value of 2.29 radians. And then we convert that to degrees. That gives us a value of 131.42 degrees. And so this then is the next position that we're going to be, in the unit circle. So 131 degrees somewhere over here, right? This is 180. This is 90. This is 180. 130 is over here somewhere, right? So then we can use that information. So let's set up our function again. So recall that we already found this. This was the first one. Now we're looking for the second one, and we're using this relationship to do it. So what we do is instead of, so since this was the first position, 0.848 radians, and we just found the second position, here, 2.29 radians, we can plug that in. We plug that in here to the function. That's going to be our next time, and solve for time. Plug the 2.2 radians in and solve for time. So okay, let's do that. So let's see, where's our function? This is the thing that we want. So this was for the first time, right? This gave us 0.848 radians, and now we just found another value, 2.29 radians minus, right, we had minus 0.4. This is fine if we just leave it unitless. Times 1 over seconds, and this gives us a value of This is T2. This gives us a value of 0.0757 radians. Right? And now we can, right. Again, sorry, I'm just ignoring the units of radians for here. This is fine because what happens is you end up with units of 1/seconds. We already looked at that. So, okay. So now what we want is delta t. So that's going to be t2 minus t1, right? That's our time interval. So what we have is, what was the first one? 0.0. So 0.0757 minus 0.0179. That's going to give us a value of 0.0578 seconds. 5.8 times 10 to the negative 2 seconds. So that's the elapsed time. And that seems very quick, right? I mean, the elapsed time is super, super short, so we're obviously talking about moving fast. And I mean, that makes sense because if we look at the angular frequency, we have 25 radians per second. I mean, unit circle is around 6 radians per second, so we're 3 times moving around a circle 3 times in 1 second. So yeah, so that's reasonable to have a value that comes out really fast. Thanks for watching.